Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Right, so let's do a little video now on the cable calculation. Now this is going to be a beginner level, so what we're going to do is we're going to do a small circuit, single phase, but do remember that the 2396, it's based on these principles and these design techniques, and what we're going to do really is just repeat what you would have done on 2382 on the 17th edition course with the cable calculation area in section 523 and 525. So shouldn't be too new. It should be just a bit of familiarization, so to speak. Your project and also in your question papers, you'll be given scenarios. And one of the most important things to do is always read the scenario. Don't read the question, read the back question. Because that's going to be filled with all the information that you need to use through your design process. So we'll go. This is just a scenario that I've made up to keep it simple for the first video. We'll do a couple more videos later, which will be obviously larger in scale and a little bit larger in challenge. So for this one, we're going to have a local garden centre, which has requested the installation of two 13-amp socket outlets, and they're going to be installed in the outside greenhouse area where all the flowers are on display. The reason for the installation is so that they have a supply. It's going to be out of reach, but it's a supply for Christmas time to plug in the tree lights and all those things. So it's just it's a socket that's not going to be used a lot, only a certain time of year. But they've requested that they be installed, ahead of time. The point of supply is a 10-way consumer unit, which is accessible where the outside greenhouse area meets the fixed building. Straight through the wall there's a single phase board. This is all in theory, just there, and so it's just a single phase board there that's 10-way. The run, that's important to know because we'll need that later on for volt drop and for a couple of other measurements, is 26 meters approximately. And being as you're outside, we're going to say that the ambient temperature in the summer is going to reach 35 degrees on average, and that's something we may need to consider with our ambient temperature. So to illustrate that, here we have an outside of a garden centre. You can just see here's the fixed building here, and I've put the board there because I can't obviously show it inside. But basically, the run is going to be coming through the wall, the other side of the wall where this board's the other side of the wall, through the wall, and along this way, and they're going to be mounted here for decorations. This is about 26 meters or so. Okay, so two 30-amp sockets being installed in the greenhouse. They're to be installed up high on the beams and are intended to supply outdoor Christmas displays. So they're not going to be used all year round, and we know that they're going to be of fairly low demand. Okay, but always make sure you've understood the scenario before you move on to start designing it. So if you look in the qualification handbook, which I linked to in the last video if you wanted to, you don't really need to, but there are design principles to follow. So we have to obviously start by understanding the characteristics of the available supply or supplies, the nature of the demand of the actual installation, the need for consideration of safety services and standby supplies. So, is your installation or your circuit going to require a safety service, standby supply, fire alarm, sprinkler, or whatever? And is there going to be a need for a standby supply, or are you going to affect either of those services? Again, we're keeping this installation very simple, so it's not really going to take much consideration there. Environmental conditions, flora, fauna, solar, we'll go through those. Once you've decided on these characteristics, you'll then choose a type of wiring system. So you're not going to say, I'm going to use PVC singles, and then realise that your environmental scenario is not suitable. Always look at your external influences to then select your wiring system. So once we've done that, we've selected our type of wiring system and installation method. We'll look at what protective equipment is needed, what isolation and switching is needed, the protected devices that will be selected. We'll consider accessibility, prevention of mutual detrimental influence, and then finally we'll do the cable calculation where we'll do the sizing of the live conductors, verification of the protective conductors. But it sounds like a lot, but it doesn't really get interesting until you're down here, really. But when you do this part, there's some information you need that you get up here. So we do need to do it in this right kind of process. So, characteristics of the available supply or supplies. Well, we're going to come from a 10-way consumer unit, accessible through the wall in the main building. It's currently 70% loaded and has 3 spare ways. I'm not going to worry too much about additional loading in this design, but having 3 spare ways does tell us that this should be a simple add to the existing demand, you know. The existing protected devices are BSCN 60898, so they're just a standard MCB. Nominal voltage is 230 volts, 50 hertz, and this is important, and you'll have this in your scenarios. Your site records show that the ZS at the CU, the consumer unit, or the ZDB, is 0.370, and the respective fault current here is 0.73 kA. And this bit, I've added this because no one really thinks about this. And I'll be honest, if you add this to your design course, it'll be a good thumbs up, because some people do forget this and a lot of trainers don't add this. But when you think of volt drop as, oh, the volt drop maximum is 11.5 or 6.9 volts if it's lighting. This is obviously on a public supplies. But you need to remember that the volt drop is total from the point of origin to the point of utilization. If we're going to actually install on a distribution board or consumer unit that is not at the origin, then we already have to accommodate for an existing allowance of volt drop. And normally we haven't got that information. This is something we should be recording on our schedules of test results now. But it's something that the clever people at the IAT and the clever people who write crap like this haven't really thought about, because they didn't think about it. But you want to know what the current volt drop is at your point of supply. So we have a volt drop to this board of 3.7 volts. So we need to deduct that from our maximum in the wiring regulations to give us a new value that we must not exceed. So these supply characteristics are very important. The number of type of live conductors, it's a 3-phase 4-wire system on a TNS system, and the supply ZE is 0.24, the PFC at 3.4. So that's fine. Not too much worried about that, because obviously we're going to come from a board that's further within the installation. The nature of the demand. Now, on a later video, we'll come up with an example or scenario where we say, oh, that 12.4 kilowatt or that 18.9 kilowatt thing, right? Then you have a power to use to find demand. With socket outlets, we kind of don't have that, and so what we do is we follow further guidance. And in this case, being a simple type of circuit, we can actually use the on-site guide. I very rarely use this because it's a bit too simplistic, but if you look in the on-site guide, Appendix A, Table A1, it actually gives us guidance for a type of circuit. And we're going to install a radial circuit, makes sense, and we're going to install a radial circuit, and the book tells us it'll be a 20 amp with a 2.5 with a 1.5 if it's MI, with a maximum floor area served of 50 meters square. Now that's obviously rounded up information. That's assuming worst case. But if we were to go with that straight away and say, oh, okay, 20 amp with 2.5, okay, that's fine. We need to remember that there are things we need to verify, such as full loop impedance and volt drop. And we also need to make sure that that is suitable a size when we consider the method of installation, because all the rating factors that are used will derate that. So this is a quick selection method. We can use it to start us off, but we can't go, that's the answer. We need to check still. So, the nature of the demand. This is actually, again, from the on-site guide. It says there that the minimum size of the conductor cross-sectional area in the circuit and in non-fused spurs is given in table H21. However, the actual size of the cable is determined by the current carrying capacity for the particular method of installation after applying the appropriate rating factors from Appendix F. they're also through the BS7671. The as installed current carrying capacity IZ, so calculated, must not be less than 20 amp for the ring, 30 amp for a radial of A2, and the one that we're going for, 20 amp for radial A3. So that kind of says what I've just actually told you already, so that we need to look at the selected or the different things that will actually have effect on the cable's ability to carry current, and we need to verify that the IZ, which is the cable that we select, that cable's current carrying capacity is more than 20 amp basically. So we're going to do that in a bit. What other things have we got to look at? Right, the supply systems for safety services and standby supplies. Small system, it's not really applicable, but it must be considered. If your run, the direction, has any impact or effect, you've got to consider that as well. But for this very simple design, we're not going to go with that yet. The environmental conditions. I'm going to be referring to Appendix 5 of BS7671, which is the external influences table. Again, as we've said in previous videos, your knowledge of BS7671 is critical for the 2396 because you use it throughout the course. You use it in the exams, it's open book, and you use it through the project. And it's the tool and the resource that the designer will be verifying to primarily. So what external influences do we have? We have the ABC, the consideration of environment, then the consideration of the utilization, so the use of it, and the construction. Alright, I've just replicated the actual contents of A. So this is all considerations of environment. And you'll see that if you go into Appendix 5 of BS7671. Now I've selected what I consider for this scenario to be suitable. So the ambient temperature, I've gone with AA4, which is -5 to up to 40 degree. Temperature and humidity isn't actually in the book. There's no tools for that. That's obviously in consideration. Altitude, not a problem. Right, water, AD. I went with jets because it's likely that although the socket is high up, there's going to be the likelihood of water getting sprayed around and probably played around with as they're going to be watering all the plants, and they may be piling them up high and they may spray them up high. It's just it's like an over consideration maybe, but it's best to over consider a little bit. Bear in mind that, you know, jets will result in IPX5. IPX5 is sometimes easier to get hold of than IPX4, so I went with jets. Foreign bodies, I went with small. Corrosion, I went with negligible. Impact, I went with low. It's up at height, so I couldn't really see any reason for there to be a risk of impact. Obviously, I am considering the cable run at the same time, which again is at height. Vibration low. Other mechanical stresses aren't currently under consideration, but you should consider other things that could occur, even like bending and things. Flora, no. Fauna, hazard. Again, I mean, flora I consider not to be a hazard, unless they obviously aren't cutting their plants as they're growing. Fauna, I thought maybe there could be the potential for rodents, but again, it's up high, so looking further, it doesn't make much of a compromise to the design anyway. But I considered that there could be a potential for rats. Electromagnetic interference, no, so that's level. Solar, medium. I didn't go with high because obviously it's not constant solar exposure in this country especially, but I went with medium just so the cable that would be chosen would have some level of it would be designed to go outside, so it'll have some level of solar radiation properties there. Seismic lightning is negligible, movement of air is low, and wind is low. So those are the environmental factors that I chose. Now you'll only know these if you read the scenario, so make sure that when you have a model design, read every word of that scenario. There'll be little nuggets of information there that will be thrown in for you to think about when you do your external influences. So that's the environment. That's the bigger one. The knock-on effect from that we'll see in a minute. Utilization and buildings. Capability I'll put as ordinary. I mean, the people using the system, I mean, they're not necessarily skilled or instructed. They're not handicapped, so they're just ordinary persons. Contact with Earth I put as frequent because they're outside. Yes, they're on concrete, but you do get a substantial amount of contact with the concrete, especially if it's wet. So if they're standing around on the concrete and there's moisture around, I put that as frequent. And I put materials of fire risk because there'll probably be some combustible materials or some wooden furniture and things being used. And same with the building structure, I put that as combustible because it's beams. So the material of the building is combustible. So when you combine all these are the ones combined that I had to consider. So the AA4 ambient, the actual regulations, if you look after the table, gives you advice or gives you direction on each of the external influences that you select. So the one that I went with, AA4, it goes normal, but you may have to have some precautions. AD5 for jets, IPX5. AE2, small objects, IP3X. If you're going to buy something that's IPX5, it'll already probably achieve IP3X. That's just a given. Hazard, again, it says depends on the nature of the fauna. So I'll be selecting equipment. It is obviously being IP35. You can't get that, so it'll be IP45 or IP55. That's going to have some substantial protection against rodents anyway. There'll be no little holes for them to creep through or anything like that. And I'll just make sure the cable that is selected is suitable for mechanical protection. So we're looking at armoured probably as our cable and wiring system of choice. You probably said that as soon as you saw it, but we have to kind of spiel all this stuff out just to actually express why we're selecting the cable that we're going for. AN2 medium, appropriate arrangements must be made for the solar and things. BA1 ordinary, it's fine, it's normal. BC3 contact with Earth, that's okay. Class 1 and 2 equipment is permitted, and the fire risk equipment is made of material avoiding the spread of flame. Obviously the equipment that we'll select will be designed to do that, and this is under consideration in the reg. So we can see from our consideration of external influences that what we're looking at really is an IP35, so 45 or 55 piece of equipment in a wiring system probably of armoured, and that is our consideration of external influences there. So type of wiring, method of installation, yeah, probably go with armoured. We'll again, what I've done here is I've gone online and I've just said that I'll use this one. This is something you should do with your design. Don't just say I'll do an armoured. Go online, look at the manufacturer's information, see where it says it's suitable for outdoor. Yeah, so this should say somewhere underground. Yeah, outdoor and indoor applications. So yeah, just make sure you get some evidence, and these are easy to save as PDFs, and you can then print them out and just put them in your project. But provide all this evidence with it. I'll go with Clip Direct as the most suitable wiring system. Makes sense. Protective equipment. Now, protective equipment you need to consider, obviously, depending on the scale of your design. If what is equipment is needed during the installation process, and obviously on completion. So, from the sake of the installation, it will require safe isolation at the point of supply, barriers and signage, access equipment. But also thinking about it, think about and put this in your design. A garden centre is going to be open to the public. So what time does garden centre open? Maybe you can start early. Maybe you can get in there an hour or so early when the staff get in, and do some of that work, and then kind of just get out of the way, clipping a cable along, and just barrier off one part of it. So think logically about the characteristics of the site, and you can actually pencil in your design a plan of work. Okay. Isolation and switching. Well, the 13632, which is the switch on a socket outlet, allows functional switching, so that's acceptable. The 60898 circuit breaker can also be used for functionality purposes, but most importantly, it can be used for isolation, so we have an isolator for the circuit. Okay. No need for emergency switching. No need for switching for mechanical maintenance. It's a very simple design, this. The protected devices, well, I'm going to be installing a socket outlet, so we now need to remember our BS7671 understanding, and a socket outlet installed, 13 amp in a public area outside. Needs to be on a 30 milliamp RCD. Yeah, so we need to make sure that that's there. There's already one at the board. What we'll need to do is maybe get the test data or do some tests ourselves to verify that it actually disconnects within 40 milliseconds at 5 times I delta N, etc, etc. Just, you can do that on your commissioning, really. But combining that with the 60898 for isolation, the 61008 RCD, jobs are good. The accessibility. No equipment has been installed, it's just obviously accessories and stuff, and all that's out of reach. Do you need accessibility for maintenance? Not really. It's on purpose that the socket outlet is out of reach, so it's not going to be often used by staff. It's a dedicated point of supply high up for Christmas displays at Christmas time. So the need for accessibility and maintainability, it's accessible for maintenance when maintenance is due, but it doesn't need to be readily accessible for use every day. So it's not too much of a problem there. Prevention of mutual detrimental influences. None, really. This is obviously where you can have grouping or other effects from adjacent cables or adjacent systems. So they both have to coexist, but one can affect the other. We get electromagnetic interference, we can get corrosion, thermal effects, all sorts of that. Again, we're going to install an armoured outside along the timber to a socket. None to consider. On the more tougher designs that will come up later, we'll start thinking about safety services, we'll start thinking about security systems, we'll start thinking about telecom systems, and we'll then start talking about segregation of band 1 circuits from band 2 circuits, and mutual detrimental influence that you can get from high frequency oscillations and things like that. We can include all that later on, but we're trying to start simple and we can then move forward. Right, we're going down to the bottom now. So we've gone through all this list. We've looked at the supply characteristics, we've looked at the nature of the supply, the voltage, the demand, the environmental conditions. We've decided what suitable protective equipment to select, what cable type to select. We now need to verify the size of that. Now earlier on it told us a 2.5mm was fine for 20 amp. We still need to verify. We can't just say, okay, that will work. We've got to verify it. Yeah, this is what it's telling us to go with already. The on-site guide is, yeah, it says 2.5, so we'll go with a 2.5 Storarama. Yeah, and that's fine on a 20 amp MCB. What else though do we need to verify? We've got to check it, considering the method of installation. We'll also verify the earth fault loop impedance, and we'll verify the volt drop and the thermal restraints. The earth fault loop impedance, we're installing a new circuit. The actual requirements of the regulations will tell us the protective measure, additional protection, will require the maximum ZS to be achieved. We really should be able to calculate that ahead of installing it. The last thing you want to do is spend most of the morning clipping in a 2.5mm armoured, then you realise when you add the ZS at dB to your value of impedance on your installed circuit that it's gone over the edge. So we should really be able to calculate the earth fault loop impedance before we install it. I did say that on my calculation video that calculation is for design, not for testing, for maintenance. We'll verify the volt drop, and we'll verify the thermal restraints using the T equals K squared S squared over I squared formula. Right, this is where you need to take it in and say to yourself, right, are you comfortable with this, or do you need to take this on board more? This is the cable calculation, cable selection process, really. So we have IB, IN, IZ. IB must be less than or equal to IN. IN must be less than or equal to IZ. You should remember that one. That's coordination. The design current must be less than the protective device, or the protected device will trip. The protected device must be less than the cable, or the cable will be overloaded before the device operates. Simple coordination. This we can calculate: design current, power over voltage. We can then select this. This, however, we need to select when we know what other factors are going to affect our cable. So we have to calculate a current carrying capacity with these factors to then select the IZ, and then we verify fault drop afterwards. But all of that starts up here. Now I haven't got a power. I don't have a power, and if I was to say 13 amp is my design current, twice 26 amp, that's not realistic, because first of all it's recommending 20 amp, and secondly we know that with diversity and stuff that we don't assume 13 amp for the socket outlet. So let's think about what the purpose of these sockets are. It's for Christmas decorations, it's for Christmas lighting displays. So what I'm going to do in hindsight, and I'll put this down in my design, is I'm going to assume each one will have a potential maximum of 800 watts, which is, I'm assuming that they're going to plug in a lead to a 4-gang, to maybe another couple of 4-gangs, because that's what these companies are like, but to a number of lights, and this should be way more than they are actually going to use, so it's kind of overcompensating as it is. Let's assume that we're going to go with 7 amp, okay, and that will be our power over voltage there. So we're going to say 800 per socket, twice power over voltage equals 7 amp. I'm going to go with 7 amp for my design current. Now I've decided to do that without actually knowing the power, so I've explained why I've made that, why I've done that thinking process. If I was to say, oh, it's 13 amp and 13 amp, it's 26 amp, that's immediately going to create a problem with common sense. Apply common sense to your design. So, fine. We'll go with 7, IB. IB must be less than or equal to IN. We would select 20 amp anyway, but it's done that for us. There is IN. Fine, great. Now, what we need to do next is identify all of the rating factors that are applicable to our installation. So, we use IT, which is a tabulated current carrying capacity, and that is the the protected device divided by whichever rating factors are applicable. So we have CA, which is the ambient temperature, CC, which is the 0.9 factor for it being buried. CD is a depth of burial. CS is the soil thermal resistivity. CF is the factor for a 3036 rewirable fuse. We've got 60898, so that's not a problem. CG is if there is a grouping factor. There's no grouping factor because we're going to be clipping this direct on the surface on its own. And CI is a factor if there's any thermal insulation either running through it or running, within 100 mil or beyond 100 mil above a ceiling, for example. Any thermal insulation along the route. So we know that none of those are applicable, but the CA for ambient temperature may be applicable. So what you would do is you go to the regulations, and all of the cable calculation formulas for these are in Appendix 4. So you go to Appendix 4, and you've got tables, lots of tables. Good page to go to if you've actually not familiar with this is in the Amendment 3 regs 331, because that introduces you to all these units. It tells you what they are. But I'm going to go ahead to the tables, and I want to go to table 4B1. Yeah, table 4B1, and first question is, what is my ambient temperature? Well, I know it's 35 degrees because that was one of my external influences. But I don't know if it's thermosetting, thermoplastic, 60 degrees, 70 degrees or 90 degrees, unless it was written down earlier on. There it is there. So it's a 70 degree thermoplastic cable type I'm going to choose. So, looking at this table, 70 degree thermoplastic, 35 degree ambient temperature, the factor of Ca is 0.94, and that is the only factor in this scenario that we're going to use. Now, we're going to do some later on, some designs later on, which will have a combination of factors. We will multiply them together. But again, all of these factors you take from scenario information, so do read that scenario very carefully. Okay, with 0.94, what we do is we take IT as IN over 0.94, 20 over 0.94. It just pushes it up from 20 to 21.3. So that means the cable that we select must be able to carry 21.3 amp and not 20 amp. This compensates the increased ambient temperature. So IZ must therefore be equal to or greater than 21.3. What we want to do is look back in Appendix 4, Table 4D4A, and this is the table for copper conductors that is for multi-core armoured cables. Now you should understand how to navigate these tables. If you watch a few more of these videos, then you'll pick that up. The reference method is clipped direct, and it's a 2-core cable, single phase. Now some people get this confused. They'll say, oh, but I'm using 3-core because I'm going to have line, neutral and earth. It's a 3-core cable. These are live conductors, so this is considering cables that are carrying current. So even if you're using a 3-core cable, it's still only really a 2-core cable, single phase. That 3rd core isn't carrying current, so you can use that column there that I've circled. Okay. We need what was the value? We need a number over 21.3. So we go to this column, 1.5 or 21, not quite enough. Next number is 28, and that's 2.5 mil. So this is actually working for us. Okay, because yeah, 2.5 mil is okay. Okay, so now that you've got that, we now need to consider the volt drop, which is on the adjacent table below. So, still 2-core cable. You'll see that there are these values here of millivolt per amp per meter. So that's basically the volt drop in millivolts for every amp that is carried for every meter that it runs. We're going with the 2.5, so that suggests an 18 millivolt per amp per meter value. So we'll take that out of the regs book. We now need to use it in a formula. This formula is written in the on-site guide, if you're unfamiliar with it. So the volt drop is the millivolt per amp per meter, which is basically this number, multiplied by the design current, we went with 7 amp, by the length, which at the very beginning told us was 26 meters. So 18 times design current of 7 times length of 26 meters over 1,000. We go over 1,000 because we don't want a millivolt value, we want a volt value. That gives us 3.3 volts. Right. Now, this isn't a lighting circuit, this is another use. So the volt drop requirement in BS7671 is for the maximum volt drop to be 11.5. But we need to add this 3.3 volts to the volts we were given earlier on of 3.7. That's 7. So that's still fine. So because the volt drop is fine overall, and because 2.5 was fine, we're going to go with 2.5. At the moment everything says 2.5 is okay. But we still haven't verified that this circuit's earth for loop impedance is going to be adequate for the requirements of chapter 41, and the thermal constraint will be okay for the full current there. We can just do these last minute checks just to verify everything's good to go. Okay, so we're going to go with 2.5. Calculation of earth for loop impedance by design. Okay, so The ZS that we're going to obtain is achieved by adding the ZSDB to the R1R2 of the circuit we are planning to install. Not the ZE, because obviously we need to incorporate the distribution circuit from the supply intake to the board we're going to use. So we're going to add ZSDB to our cables R1R2 to give us a ZS. This is calculation by design to verified design. So we go with a 2.5. Again, in the on-site guide it tells us, there's a table in the appendices, table L1, that the R1 plus R2 per meter, in milliohms per meter, for a 2.5 and a 2.5, so that's a 2.5 line and a 2.5 protective conductor, is 14.82 milliohms per meter. So 14.82 milliohms times by a length, because it's per meter, of 26 over 1,000, because we don't want milliohms, we want ohms, suggests that the circuit we're about to install will have an R1 and R2 of 0.38. We'll add that 0.38 to our supply point ZDB, 0.37, will give us a maximum of 0.75. Again, this is where we calculate ZS at the design stage to see how close we are to the values according to the wiring regulations, which if you look in BS 7671 in the tables in chapter 41, it'll tell you that a 60898 20 amp type B has a maximum full loop impedance of 2.19 ohms. Therefore, this looks to be perfectly acceptable. It's nowhere near on the limit. So ADS, additional automatic disconnection of supply, should be satisfied by this design once we verified RCD disconnections as well, because of the additional protection requirement. Okay, so this is an earth full loop impedance verification. What else can we do? Thermal constraint. We verified the live conductor is suitable to carry the load according to the length with its method of installation. We have then verified the volt drop will be allowable for the length and the design current. We've then verified that the circuit that we design's earth full loop impedance will be adequate to achieve sufficient fault current in an earth fault to disconnect that circuit within the required time frame. But we'd like to just check also, depending on the supply fault current and everything, is that the actual current level that will be there will be okay for the insulation on the live conductors. Because remember, with an earth full loop impedance, you're verifying the protective conductor route with the thermal withstand. You're going to verify that for the live conductors as well, so for a short circuit condition as well. So the maximum disconnection time for the final circuit under 32 amp on a TN system will be 0.4 seconds. That's fine. That's in the regulations. If you go to the curves in Appendix 3 to the BSCN 60898 type B curve, figure 3A4, it will tell you that for a B20 amp to disconnect in 0.1 to 5 seconds, it will require a total current of 100 amp. That's it. So 100 amp is enough to disconnect. So the thermal withstand formula, T is time. This is calculating the time that the circuit has to kind of turn off, because when we've got to this time or before, the conductor's insulation material will start to become damaged due to the thermal stresses, the amount of heat or build-up of temperature on the conductors during this fault condition. So this is all in, this formula is from chapter 42, I think, protection against thermal effects. That's where T equals K squared S squared over I squared exists. And what it is K squared is 115. This is determined by the cable choice that we're going for. Look at the tables in that area for that. Times S, which is the size of the conductor. And we go with 2.5. That's what we've gone for. Over I squared, which is the amount of current that's going to be flowing in this incident. So 115 squared times 2.5 squared, if you're doing it on a calculator, get that value sum or put it in brackets, divided by 100 squared. I get 8.26 seconds. This tells me Right, the circuit I've installed, which should disconnect in 0.4 seconds, and an earth fault probably in 0.04 seconds of the 40 milliseconds. This tells me that when I put a fault condition of up to 100 amp through the circuit I'm installing, it will take 8.2 seconds for these live conductors, or these 2.5mm conductors, to now start softening and becoming damaged. The thermoplastic insulation will start to suffer. So it must turn off within 8.2 seconds, which we verified now that it does with all of this earth fault loop impedance and verification of fault current there. Yeah, so what else can we do? We can verify the protective conductor size. Why do we need to do that? Well, what we need to consider is that amount of energy, that current, because bear in mind this was verifying the live conductors with the disconnection. This is verifying that that earth can carry that amount of current for the duration. Yeah. So for the earth to be able to carry this amount of current for this time, how big does it need to be? So we're going to calculate the minimum required protective conductor size, and this is in chapter 54, I think, the adiabatic equation. So S is equal to the square root of I squared T over K. It's same data as before. What is the fault current? 100 amp. What is the disconnection time? 0.4 seconds. Okay, maximum disconnection time, 0.4 seconds. So 100 amp within 0.4 seconds over 115, which is the factor. This gives us a value of 0.549, which isn't the cable size, so we have to go up to the next one, which is for solid cables, 1 mil. Therefore, the protective conductor must be a minimum of 1 mil to be able to carry 100 amp within 0.4 seconds, or it will be damaged. We are going to be using a steel wire armor with a 2.5 mil, so our earth is oversized, but it comes in the steel wire armor, so jobs are good. But we need to verify this. We need to just record this information so that we've actually got traceability with our design. So to conclude, the circuit will be wired in a 2.5mm steel wire armor clipped direct to the timber. The accessories we will select will be to a minimum of IP35. We will verify the effectiveness of the existing RCDs. So think about your RCD times. So, you know, times 1 times 5. Verify that they work. It will require times 5 due to the fact that it's a socket outlet being installed with the additional protective measure. So do verify that. We will produce an electrical installation certificate because it's a new circuit, completed with the schedule of inspections and the schedule of test results. All test measurements will be compared with the design criteria. We'll also obviously provide all of the information, the cable manufacturer information, the accessory information, the manufacturer's instructions, and all of that will go into our operational manual. And if you're thinking that's a mouthful, that's what we have to do with any design, is provide an operational manual. Obviously, the bigger the design, the bigger the manual. Alright. I think that's the end of this. Yeah. So, that's a small scale installation. Have a little play with it. Understand the journey. Understand the journey. You know, selecting the external influences, the supply characteristics, and then when you come to this part, the process IBIN, rating factors, calculate IT with the rating factors. Having calculated IT, select IZ, then verify volt drop. Understand that sequence. We're going to do again a video very soon, moving this up another little notch. Okay, guys, but yeah, have fun with it. Just start coming up with your own scenarios. You know, if you're doing the 2396, you know, you can ask the tutor for some examples and questions, but you don't need question papers really. All you got to do is just pop up with some random stuff. You know, think of a type of environment that you've not worked on before. When you come to the length, random number. You can even use a random number generator on the internet. Okay? Cable types, just randomize it and then decide to put it all together to see if it makes sense and if it will work. Sometimes it will, sometimes it won't. Most often, the ones that you know won't work when you actually say what you're putting, you'll be able to prove that they won't work. Alright? But have a little play with it. see how far you go, and I will see you in the next video, which is, I think, outcome. Is it the rest? Yes, the rest of outcome 2, 2.2 onwards. Good stuff.